Today on the Blue Planet Spacecraft Club. Oh, Mechanics Illustrated. Ooh-wee, February, no, January, 25 cents. America's plans to conquer outer space. What year is this? Oh, 1956 of January. Well, let's see what it has to say. All aboard for outer space. This is the ship that will take us to Earth's first manned satellite. Alright. On May 24th, 1954, a Navy Viking rocket thundered 158 miles into space. As recently as February 1949, a V-2 WAC Corporal Bumper rocket soared 250 miles into the sky over New Mexico White Sands Proving Grounds. Last year, an Air Force pilot flew the Bell X-1A rocket plane above 80,000 feet and at more than twice the speed of sound. Well, they're getting there. We have built rockets which have gone beyond Earth's atmosphere and returned. They have reached altitudes where the remnants of the atmosphere around them were a better vacuum than in a radio tube. We have sent men to altitudes where their blood would boil if they were not protected by a pressure suit and a pressurized cabin. Soon we'll go into space and stay. We have performed all the necessary theoretical work. We know how it will be done, and we can foresee some of the problems we will encounter. We are working with prototypes of the devices which will finally overcome the greatest barrier of all, gravity. What remains now is only for the engineers and scientists to make final steps, and they may already be making them. The race for artificial satellite and space flight is on. In this greatest adventure of all history, America's pride and national prestige is at stake. There is no doubt in our minds of our rocket scientists and guided missile engineers that a satellite can be placed in space. They want America to do it first because, as free men, they want others to enjoy the freedom we have. We would use our satellite to prevent war. We'd also use... let's see here. We would also use it for peaceful research in chemistry, electronics, astronomy, physics, cosmic ray biology, and a host of other fields. Our national reputation is such that we may even offer services of the satellite research laboratories to other nations, much as we are doing with our atomic research in President Eisenhower's Atoms for Peace program. Alright, an unmanned satellite will be first. Then we'll build intercontinental ballistic missiles and may have to run extensive experiments with manned rocket planes such as the Bell X-1A or bigger. But in the not-so-distant future, a manned satellite will circle the Earth in space. To transport men and equipment to the manned space station during orbiting around Earth, we will have to have great towering ships powered by banks of rocket engines which gulp up tons of fuel every second. Many rocket men, Dr. Werner von Braun being the foremost, have conceived huge three-stage rocket ships capable of making the flight to the space station. But recently, a group of engineers from the Goodyear Aircraft Corporation told the American Rocket Society in New York how to do it easier, cheaper, and more reliably. These three men, Darrell C. Romick, Richard E. Knight, and John M. Van Pelt, are working today on super-secret government rocket projects. But as with many of their colleagues, they are very serious about the coming age of spaceflight. Darrell C. Romick, for example, is chairman of the American Rocket Society's 1955 Space Flight Symposium held in Chicago in November. Their technical paper entitled A Preliminary Design Study of a Three-Stage Satellite Ferry Rocket Vehicle with Piloted Recoverable Stages. That sounds familiar. Elon presents a new approach to the old ideas and concepts of spaceships. Rocket people have known for a long time that a rocket which could escape the Earth's gravity would have to be a big one. would have to be big. Alright, some engineers have calculated that over 99% of the weight would have to be fuel, gallons and gallons of liquid oxygen and alcohol. But back in 1929, an Australian scientist named Herman Oberth developed a theory of the step rocket. Essentially, this theory is simple. With a single-stage rocket such as the V2 or Viking, the rocket engine must push the entire ship, including those fuel tanks, which are already empty and therefore useless weight. The step rocket principle merely states you must throw away what you no longer need once its usefulness is exhausted. This simple principle means that a ship will have to use less fuel to lift the same amount of payload away from the Earth. In fact, the step rocket principle makes space flight practical. And the principle has already been checked and proved with the two-stage V2 WAC Corporal bumper rocket, in which the WAC took off from a nose of a V2 at high altitudes after the V2 had exhausted its fuel. The V2 alone was capable of reaching 132 miles. The WAC by itself could reach about 50 miles. Together, they did not reach the sum of these 182 miles, but an altitude of 250 miles. But when these used portions of the spaceship or step rocket, the lower stages or boosters separate from the rest of the craft, they fall back to the ground again. The recovery of these big, complicated, and expensive boosters has always been a problem. Scientists suggested that launching sites be located on sea coasts to allow the boosters to fall in the ocean away from densely populated areas. That makes sense. Some schemes have been present for recovering the boosters by parachutes. However, the three Goodyear engineers have designed a three-stage spaceship whose boosters are manned with crews and flown back to the ground as gliders. Roughly, their system would work like this. The three stages of the spaceship are assembled at White Sands Proving Grounds, where final checkouts are performed and the ship readied on the launcher. Riders up on the elevators inside tall loading towers, and the three separate crews aboard the ship, one crew for each stage. The 35 tons of cargo payload have already been placed aboard the top stages, which will be the only one to reach the space station. Final checks are made with the crews running pre-lift tests at each section of the ship. At 0 time, the 9,000-ton ship will lift, driving the clusters of rocket engines in Booster 1, a lower stage, producing 16,000 tons of thrust. The crew in Booster 1 will be in complete control at all times. But if an emergency occurs, the three stages can be separated, each to find its way to a safe landing under the control. The ship tilts slowly to the east, and after 90 seconds, all the propellant in Booster 1 is used up. The first separation now occurs with the upper two stages being ejected forward. Holy cow. I'm just going to let you read that. Have to pause it. Alright, and we'll do a part 2. Thanks.